and try to develop metrics for habitability. So I find this result delightful because it makes me have to expand my notion of what environmental constituents might enable habitability. So for example, if you just think about an environment in terms of what it's made of and how those things are arranged, you have a concept of an environment just like the chemical environment. Everything is a function of its constituents and how they're arranged. So what is really interesting about this result is if you can make a biomolecule that has substitutions in it, the properties have to change as a function of new constituents. So it opens up a whole new line of questioning. What might those changes be? What do they portend for the evolution of that chemistry? What do they mean about the environment? And by the same token, we might learn something new about habitable environments by understanding how organisms that are there adapt to the presence of new or limited chemical constituents. With respect to space exploration, this is a very interesting result again, because the implication is that we still don't know everything there is to know about what might make a habitable environment on another planet or a satellite of another planet. We have to increasingly broaden our perspective. So perhaps arsenic is not an essential component for habitability or for life, but it may be one that can be tolerated, and that opens up our perspective to try to understand what other potential components might be tolerated, or in fact even essential, that we presently haven't thought of.
Thank you very much. So I'd like to bring this all around and back to Felisa, for her to put her findings in a broader context for us and remind us of exactly what they are and their importance.
So let's remind us what we've learned here today. I'm interested in exceptions, and I think many of us are interested in those exceptions to the rules. Why are things constants in nature? That keeps me up at night. Why? I was probably a very difficult child in junior high and high school. But what I'll say is that that kind of openness to questions is part of what I want. I hope that the work of myself and my team that produced this. What I want to really reiterate is it's not about arsenic, and this isn't about Mono Lake. It's about thinking about life in a planetary context and asking questions, simple questions, with a simple experimental design. And so in like a bigger scale, let's go from the small and then we'll go into the abstract. All life on Earth required carbon, nitrogen, oxygen, hydrogen, phosphorus, and sulfur. So I've shown here today that we've discovered a microbe that can substitute arsenic for phosphorus in its major biomolecules. Not just DNA, but things like ATP that many of those high school students out there I hope recognize, and also all sorts of other biomolecules. What does that suggest? It cracks open the door to the potential. You know, my niece asks me, how did we get here? And are we alone in the universe? And it's profound that we don't know the answers exactly to that yet. Maybe not in my lifetime, but maybe in her lifetime, she'll be able to answer that. But I hope my work serves as a proof of concept that we can experimentally test and show evidence of what else is possible. So I'd like to roll some footage just to give us the expansive nature of life, from microbes to crustacea, to bugs, to mammals, to everything you know that's alive on planet Earth. Again, hearkening back to the idea of the pale blue dot. Understanding life here, all sorts of life, lions and tigers and bears. And how everything we know is on this tree of life. Everything you've ever thought of so far that we can see on this tree of life. So what we're presenting here today is a member of this tree of life. We're cracking open that door. Strain GFAJ1, the bacterium, is a different way to do business, just to open the possibility to what else is possible. It has solved the challenge of being alive in a very different way than we knew of. What other questions can we ask? This will inform us about life on our own planet, and it will help inform us of life. We will find it one day elsewhere in the universe. Thank you.
Thank you very much, Felisa. And now I'm going to turn it back over to you, Dwayne.
Thank you all. And Felisa, congratulations to you and your team. Okay, ladies and gentlemen, now we get to the question and answers to really even flush it out even more. We're going to start here first and then go to the West Coast. I'm going to ask you to wait for the microphone, give your name and affiliation, and obviously we have folks here, and we also have a professor in Arizona, so if you can address your question to the appropriate person, that would be great. Let's start with Mark Kaufman.
Thank you, and congratulations. What I'm intrigued by and trying to understand is you refer here to substitution of the arsenic. Is there reason to believe that this was substitution that occurred in any kind of a time frame, or is it possible that this is something that has been in the bacterium or in other bacteria going back to the beginning of time?
That's a great question. And I think, you know, we'll have the next 30 years, at least of my career, and many others to begin to probe that. I think what it does suggest, I'm saying substitution, because we really just want to open this package to be able to think about what else life could be. And as an early career scientist, I think that's a safe way to go. But in terms of whether I think if it just happened recently, substituting for what was, or how old this is, I think we can begin to address those questions. There's a number of experiments I can think of, and I know many of my colleagues who have been familiar with this work for a number of months now have suggested. What we can say, and dangerously to speculate just a little bit if you'd let me, is that phosphate, and it's phosphate in biomolecules, so phosphorus, and I'll go between those, you'll have to pardon me, on Earth is locked up in rock. So your bones are made of phosphate, because it's a good idea. And it's very, one of the reasons it just doesn't do a lot of chemistry. And in fact, I hope that Steve would agree in that phosphate chemistry is very difficult. And we can speculate a little bit about, can be very difficult. We can speculate about, and we have no evidence of how life yet started. Okay, given that, there are a number of scientists who've proposed that in hydrothermal vent systems where we have a gradient, so different chemicals coming together, arsenic would have been available for prebiotic chemistry. Whether it was or not, we can't speak to, I wasn't there, but it does chemistry rapidly. It can do chemistry more rapidly. So I think that it will be a fun thing to try and test, but it's not an easy problem.
Randy Shostak, reporter with EOS, the newspaper of the American Geophysical Union. How does and might this finding affect NASA's and others' astrobiology programs, including the Mars Science Lab and other ongoing and planned missions and programs?
Do you want me to?
You can start.
All right, I'll start then. With respect to Mars Science Laboratory, or in general, the problem of studying habitability on other planets, the way that one could be affected is to think more broadly about what sorts of environments one might characterize as habitable. In specific, with respect to experiments that we could do on Mars Science Laboratory, we do have payload investigations that can measure the chemical elements. We do have a payload investigation that I'm associated with that can actually measure organic molecules. So one way that you can tell what you have is by putting together a number of investigations. And like all science, independent lines of corroboration help you paint a bigger picture. So for example, on Mars Science Laboratory, if you had an environment that appeared to be rich in arsenic or some unanticipated metal, and you also had a finding of organic molecules, you could begin to put a picture together about what the environmental chemistry might portend.
And I'll take a shot at that. I think this finding points to a challenge that we've known we've had for a while. Clearly, if we went to another planet or another body in the universe and we saw a human, we would recognize it as life. And there are many other forms we could probably recognize. The challenge of finding something that is significantly different than terrestrial life and life as we know it is really what plagues us when we think about spending the money that we do, developing the instruments that we do, and sending them off on a mission. And so I think it's been our strategy with the support of the scientific community to think as broadly as possible, to put measurements that we may deem reasonable in a context, so make a context of the environment, to explore possibilities that are not so focused on a specific molecule. For example, we would not want to at this point necessarily go to look for specifically DNA that had arsenic in its backbone. We want to keep them very broad and keep our strategy in seeking signs of life open to the possibility of things. We would hate to go somewhere and not see it.